Hi, section 3.6, the chain rule. The chain rule is one of the most important rules in calculus. With the chain rule, you can get derivatives of very complicated functions. It's very important. Let's begin with this example. Differentiate the function. Okay, we have 3x squared plus 1 squared. So once you want to get the derivative of the function, then you may expand it so that the expanded formula for f can be written in this way. Now this is a form of a plus b squared. So a squared plus 2ab plus b squared. So we can reach that formula. Now you can differentiate it by using the power rule so that you can reach that derivative. You can do this way. Now we'll try a different way. Okay, we introduce a new variable u, which is now 3x plus 1. That is this portion. Then f of x can be written as u squared here because we replace this portion by u, so that becomes u squared. Now we look at the derivative. Derivative is a rate of change of f with respect to x. That quantity is the limit of this average rate of change. Change in f divided by change in x, and then we take the limit by approaching the change in x 0. Change in x is approaching 0, then if the limit exists, then we say that is the derivative we did. So we may consider this df over dx really like a fraction. So in fact, this is a limit of the fraction. So yet we may consider it as a fraction. Then we may introduce another one so that this fraction, that fraction multiplication will be same as original one. Or you may think in this way. This is a ratio, rate of change, ratio. But now, by using an intermediate the term, you can measure the ratio between the original one, the top one, and the mid one, and then now ratio between mid one and bottom one, so that eventually the ratio multiplication is the same as original one. You may think either way. Okay, now we'll try to use that formula. Then here u squared, now that is differentiation with respect to u, so that is f is u squared, and with respect to u, and differentiation is simply power rule. That is 2u. And now u itself, okay, with respect to x, then that will be 6x. Now u is this term, so we replace it so that, okay, that's a 12ux, and u is replaced by the original quantity here. So we reach at that this one is the same as now that one. So for this example, and this may not be, this way is not be, may not be beneficial because almost the same complexity. Now, what if you are thinking, for example, now fx equal here same u and 3x squared plus 1 and to the 10. How about that? Then, now for this one, if you try to make expansion, then it's a long So it's not really easy. However, if you're using this formula, then okay, that can be written as u to the 10, so that df over dx is the same as, now df over du is, by using the power rule, we can get 10 times u to the 9, and here du over dx is the same here, 6x. Right? So that can be written 60 times u to the 9 and x. What is u? U is 3x squared plus 1, so that we can get here 60, here 3x squared plus 1 to the 9 times here x. That's it. Quite simple, right? So the chain rule is really will make you get derivatives much more easily. Okay, here we have theorem, the chain rule. If f of u is differentiable at u, and also u is g of x, that means a function of x. Now also g of x is differentiable at point x, then here the composite function is differentiable at x, and here we have now, and the composite function derivative with respect to x is the same as f derivative with respect to g of x. Now inside of parentheses, the g of x is given, which means that the derivative is with respect to that g of x, times g prime x. Now that derivative is with respect to x. Explicitly, we can write in this way: d f of g of x over dg of x. So differentiation is with respect to g of x. And now for g of x, we can take now derivative as usual. And that is the here the chain rule. And we can prove it quite easily here. Now proof is given. Now for that one, the simpler form can be written this way: dy over dx as dy over du times du over dx, so that is also Leibniz notation. So using dy dx, such a format is called Leibniz notation. Okay. Now here for the proof, we'll consider now y equal f of u, which is same as f of g of x. We define delta u as the difference, and here we can easily see that g is also differentiable, so that once h approaches 0, then that delta u is also approaching 0. And here in definition, dy over dx is the same as, now here for the composite function here x plus h and x, and that difference divided by h. That is definition of derivative with respect to x. Now here g of x plus h can be written as g of x plus delta u. So we put here now. Okay. And that difference is here now delta u, and this is h. So we try to put here delta u, and we are trying to put delta u over there and divide by h, so that after canceling, we can get the same quantity. Now, if that is multiplication, if for each term, if limit exists, then we can apply the limit separately. So we put here limit here, and then limit. Okay. And now, as h approaches 0, we already know that delta u approaches 0, so that the limit with here h approaches 0 is the same as now as delta u approaching 0. Okay, again, delta u is, the definition is written. Okay, here now, that is the same as now derivative with respect to here g of x. Delta u is basically a change in g, so that now this term is the same as derivative of f with respect to g, and now this term is the same as derivative of g with respect to x. So we can reach at this one. Okay. So here we'll try to use this formula in this section. Okay. Differentiate sine x squared plus e to the x. And for that one, here inside this parenthesis we have x squared plus e to the x, so that we may introduce u equal x squared plus e to the x. Right? Then the given function, let's say this is f, then f can be written sine of u, so that df over dx is the same as df over du times du over dx. Okay, df over du. Now u is the variable, so that derivative of sine is cosine, so that is cosine u times du over dx. Now we have to get x derivative. Then for x squared it becomes 2x, and e to the x remains the same, like that. We are not done yet. There's u involved, so you have to replace everything by using only x variable. U is our intermediate variable to use the chain rule, so that you have to now use the definition to eliminate u. So that is cosine now x squared plus e to the x, and here times 2x plus e to the x. That's the final answer. Okay. Now we'll try to find the dy over dx, and again same by first writing the function in terms of in form of f of u. Okay. Now that can be written if we are using u equal x cubed minus 1 over here. Now just a moment, let's write again, x cubed minus 1. Okay, then it can be written u to the 100. Right? Okay, now dy over dx is same as dy over du and du over dx. Okay, so here now dy over du, u to the 100. By using the power rule, we can get 100 times u to the 99, 100 minus 1. Now times du over dx, which is 3x squared. Okay, so here the constant is 300. U is here now x cubed minus 1 to the 99, and we have here extra x squared. That's the answer. Now let's go to C. Now that one is again, this can be written as once we are introducing u equal tangent x, then now it can be written u to the 3. Okay, so dg over dx is the same as dg over du times du over dx. Okay, now u to the 3, and now u derivative is 3u squared times du over dx, tangent derivative is sec squared x. Now we have to replace u with the original definition. So it's 3 times. Here, that is tangent. Now squared x, and here sec squared x. Okay. Okay, for that one, again, it can be written if we are using u equal 2x squared, then that can be written here sine of u. So now dy over dx, okay, let's do it now here without writing, just the dy over du, that is, which is cosine u, times du over dx, which is now 4x. So that cosine u is 2x squared, and here 4x multiplied. Again, the same for that one. If we are using u equal here 4 square root over x plus x squared, then now this function becomes here now, that is e to the u. Okay. So here dy over dx is same as, okay, let's write down the formula, dy over du times du over dx. Okay, u derivative of e to the u is same as e to the u times du over dx, x derivative. Now square root of x is basically, okay, yeah, let's try to get a derivative for square root of x. Square root of x, now which is same as x to the 1/2 power, so that if we are making the differentiation, then there is half and x to the minus half, which means that that is 2 square root over x. Okay. So here, and 4 is multiplied, so 2 over square root over x, and here derivative is 2x. And again, u must be replaced by original term, so e to the 4 square root over x plus x squared times, now here 2 over square root over x plus 2x. Okay, that's the final answer. And in many cases, we have to apply the chain rule 2 or more times to find the derivative. Okay, here for this one, now if we are using u equal, for example, here e to the cosine x, and now plus 1, then it can be written square root of u. So here dy over dx can be dy over du times du over dx. Okay, here we have, now that term will become, earlier we know that here now, for square root of x, x derivative changed in this way, so that for this term, u derivative will be 1 over 2 square root of u, now times here du over dx. Okay, that is du over dx of now e to the cosine x plus 1. So here again, we have to get the derivative of that by using one more time of chain rule. So now we are using one more time. Now in this case, we try to use a v variable. Then once we try to get v equal cosine x, then e to the here cosine x plus 1 will be e to the v plus 1 here. And so this whole term d over dx and e to the cosine x plus 1 can be written, okay, this term anyway, and over du, okay, we'll put here the same term, and okay, dv, okay, dv, same term here, dv times dv over dx. Now, along with the v derivative, it'll become e to the v, and times, now v x derivative is the same as minus sine x. Okay, so we can reach it here now. That is e to the now cosine x, and okay, negation here, times here sine x, right? Okay, so we can put here over there, then eventually dy over dx, that is the same as, okay, 1 over 2 square root of u is given in this way, so that 1 over 2 square root of u is now e to the cosine x plus 1 times the derivative of e to the cosine x plus 1 is obtained here, that one. So that is now, okay, we put here now minus, and e to the cosine x times here sine x. It's a little bit complicated, but the idea is that we can use the chain rule more than once to get the derivative. So in this case, we used twice the derivative, the chain rule. Okay, now for this problem, and this is product, this term and that term, so we are using product rule and chain rule to get the here derivative. Okay, y prime, that is first, and that is a sort of f times g, so that the derivative is f prime g plus f g prime, right? That is product rule. So that derivative is same as here minus 2, and then now, okay, you have to use chain rule. First, you are considering now that as a variable. Then along with that variable, here derivative, then here minus 2 will come out, and 2x minus 5 and power is minus 3. And then that variable derivative, that's 2. That is f prime. This portion is f prime, and g, that is x squared minus 5x to this x. And plus f is here 2x minus 5 and minus 2. Now, okay, we consider this portion as u. Then anyway, we have to make the derivative, whole thing derivative. So that's as variable u, or you may think some a variable, x squared minus 5x is a variable. So that along with the variable, if you are considering this whole thing from here to there, then that is simply just the variable 6 to the power. So the derivative with respect to variable will be 6 times the variable x squared minus 5x to the 5. Now, the variable must be differentiated with respect to x, which is now 2x minus 5. If you want, you can simplify, but that is the solution. Okay, let's try to find the derivative of the following functions. For that one, okay, here, and we'll do it, this problem with our, just rather than writing the variable, intermediate variable explicitly, we'll consider the intermediate variable many times and try to get the derivative here. Okay, y prime. First, we are considering sine squared t pi t minus 1. That whole thing is a variable. This whole thing, the exponent is a variable. Then derivative with respect to variable is the same as the original one. So that is a sine squared pi t minus 1. Now, so we have to multiply here the derivative of the variable with respect to t, so that there's now d over dt of that portion sine and squared. Now, okay, it's not t, pi t, and here that is pi t minus 1, right? Okay, we have to do it. Okay, again, now for that portion, this is t derivative. Now we are considering sine pi t minus 1. We consider sine pi t minus 1 as a variable. Then that is a variable squared. So this term is the same as 2 the variable. So that is now sine and pi t minus 1. And then now you have to multiply here d over dt and sine pi t minus 1. Right? It's a little bit complicated. Now again, we are considering pi t minus 1 as a variable. Then this derivative, okay, let's try to use a different color here. So that this term also, that is the same as, in fact, this term right now. Anyway, yeah, this term, we consider now pi t minus 1 as a variable. Then this derivative will be here now. Okay, that will be here cosine the variable pi t minus 1 and the variable derivative with respect to t, which is pi. So for this problem, we use the one chain rule. Now here we have one more time, and now we have one more time of the chain rule. So along with this multiple application of chain rule, we reach that. Of course, we can finalize the answer here in this way. Start with e to the sine squared pi t minus 1. Now, that term is same as this one, so that twice of sine and pi t minus 1. And again, this term is changed in this way, so it's a cosine now pi t. Oops. Pi t minus 1, and finally we have a pi. It's a little bit long. However, anyway, we can get in this way. Okay, also the same. Okay, let's try to solve this problem here. And there's b now. y equal here cosine fourth power and sec 4t. Okay, for this function, first we consider that is a variable. No, just a moment. And earlier than that, we consider cosine sec 4t is a variable. Then that is the variable fourth power, so that y dy over dt is same as the, okay, so once cosine sec 4t is a variable, then that is basically the variable to the 4. So that is the same as 4 times the variable and third power, so which is cosine now third power and sec here, okay, sec 4t cn 4t. Okay, and then we have to put here now t derivative of the variable. Okay, so it's a d over dt of cosine now sec 4t. Okay, again we are focusing on this portion, and now we are, okay, this portion, and we think this is a variable. Then cosine variable, and here with respect to the variable, cosine in derivative becomes minus sign, so that this portion is same as minus sign of the variable times now d over dt, the variable. Okay, here again for that one 4t is a variable, then sec derivative is sec times tangent, so that is same as sec 4t and tangent 4t, and now the variable t derivative, which is 4. So now we combine everything. So from here we have 4 here, 4 here, so that is 16. Now this cosine third power now sec 40, and we consider here now we have a minus. Okay, let's put here now minus here, and then sine now sec 40, and this portion is same as sec 40 and tangent and 40. Wow, it's a little bit complicated. However, this is the chain rule. By using multiple times of chain rule, you can get the derivative. Okay, this one is simpler, so that you can do it yourself. Try. Okay. Okay. So here, in this example, we try to get the derivative. So it is basically in this calculus 1 level is most complicated problem in some sense. But anyway, we tried to get the derivative. Okay, here we have find the value of f, the component z, the derivative at the given value of x. Use this to find the equation of tangent line to the curve at the given point. Okay. Now, the composite one, so that here u is defined to be square root of x. So that if you are making x derivative, df over dx, then here df over du times du over dx. That is the formula. Now, okay, in terms of u, f can be written this way, so that u derivative will be 5 times u to the 4, and then u x derivative is, for that one, here 1 over 2 square root of x. Okay, so that will be changed into here u to the 4 is same as x squared, so that 5 x squared now times 1 over 2 square root of x. So it is negative half of power. So now the coefficient is 5 over 2 and x to the 3 over 2. Okay, that's the derivative. Now here, when x equal 1, now we know that u equal 1, and then here f here f of u g of 1 basically, so that complete function g of 1, which is f of 1, and then 1, and then the values 2. So that for the complete function, the point is here now 1 and 2, and at x1 here slope is here x is 1, then the value is 1, and now there's 5 over 2. So here the equation of the tangent line can be given in this way: y minus y0, so the y minus 2 equal the slope 5 over 2, and x minus x0, which is 1. Okay, this is the answer. Now we have a challenge problem. Okay, verify each of the following statement. Let's focus on part A. Once f is even, then f prime is odd. And other way, here f is odd, then f prime is even. So you have to prove that. In mathematical proof, in most cases, you have to start with a definition. Mathematics start with a definition. What is even? Assume in the beginning for that portion, f is even. Then that means that by definition here, if you try to measure f value at minus x, then that is the same as at x, like that. Now, the target in the proof is that this is assumption, along with that assumption, but this assumption is the same as that. Now, from this one, what you have to prove is f prime is odd. So you have to make it here derivative. You are applying the differential operator both sides, then you'll see easily that here you can conclude quite easily. So always mathematics start with a definition. So from this one you can conclude this quite easily. Again, now f is odd. For that one, f is odd. That is the same as, in definition, is same as f at minus x. The value is same as negative over f over x. Start with your assumption is this one for part B. And now if you are making derivative, now the derivative is with respect to x, then you'll see the derivative will become even. So just simply do it and try to interpret it, and that's it. Okay, this is the end of the section. Thank you.